Today we study three special families of matrices: diagonal matrices, triangular matrices, and symmetric matrices. The goal is to recognize their structure and use that structure to make computations easier. A diagonal matrix is a square matrix where only the main diagonal may contain non-zero entries. Everything else must be zero. This special shape makes diagonal matrices very easy to work with. To invert a diagonal matrix, invert each diagonal entry. This only works if none of the diagonal entries are zero. So diagonal matrices are nice, but they still refuse to divide by zero, like the rest of mathematics. Here we compare two diagonal matrices. The first is invertible because every diagonal entry is non-zero. The second is not invertible because it has a zero on the diagonal. 1 0 is enough to ruin invertibility. Taking powers of diagonal matrices is very easy. We just raise each diagonal entry to that power. Notice that -2 squared becomes +4. Left multiplication by a diagonal matrix scales rows. The first row is multiplied by the first diagonal entry, the second row by the second diagonal entry, and so on. Right multiplication by a diagonal matrix scales columns. This is a useful shortcut. Left means rows, right means columns. It is one of those rare rules that is actually easier than doing the full multiplication. This example shows both types of scaling. Multiplying D times A scales the rows of A. Multiplying B times D scales the columns of B. The sizes must match, otherwise the multiplication is not defined. Triangular matrices have zeros on one side of the diagonal. Lower triangular means the non-zero part can be below the diagonal. Upper triangular means the non-zero part can be above the diagonal. Diagonal matrices count as both, because they are very well behaved. This slide lists the main structural properties of triangular matrices. Transpose switches lower and upper. Products preserve the same type. Invertibility depends only on the diagonal entries, and the inverse keeps the same triangular shape. This is the compact version of the triangular matrix rules. The important warning is that the inverse statements only make sense when the matrix is actually invertible. Before computing the inverse, we already know two things. It exists, and it will be upper triangular. This is the advantage of recognizing structure before doing computation. A symmetric matrix is equal to its transpose. The entries mirror across the main diagonal. So the upper right part and lower left part match each other. Symmetric matrices are closed under transpose, addition, subtraction, and scalar multiplication. So if we combine symmetric matrices using these operations, we stay in the world of symmetric matrices. This is a common trap. Even if A and B are both symmetric, their product does not have to be symmetric. Matrix multiplication is not as polite as addition. The product AB is symmetric exactly when AB equals BA. This condition is called commuting. For numbers, multiplication always commutes. For matrices, not so much. Matrix multiplication prefers work from home. If a symmetric matrix is invertible, its inverse is also symmetric. This follows from the transpose rule for inverses. The symmetry survives inversion. No matter what shape A has, the products AA transpose and A transpose A are symmetric whenever the products are defined. These matrices appear often in applications, especially statistics and optimization. If A is invertible, then a transpose is invertible too. Since a product of invertible matrices is invertible, both AA transpose and A transpose A are invertible. The main takeaway is to look at the shape of a matrix before doing long computations. Structure can save time, reduce mistakes, and occasionally make a problem almost too easy. Almost.